So what is queuing network model or system execution models, right? So previously we talked about the software execution models, right? Provide a static analysis of the mean, best, and worst case response time for software, right? It characterizes the resource requirements of the proposed software alone in the absence of other workloads or multiple users. It doesn't consider when there are many users using the system at the same time, right? So what is a queuing network model, or also called a system execution model? It actually characterizes the software's performance in the presence of dynamic factors such as other workloads or multiple users. It also aims to solve the contention for resources. So queuing network models allow us to analyze, for example, the executing time of the system when there are like many users using the system at the same time. Okay. So when there's only one user using the system, for example, it takes 1 millisecond to process one search, but when there are 10 users using the system at the same time, maybe the speed will be slower, right? That's kind of easy to understand. So then let's discuss what is a queuing network model, okay? And before that, we want to understand like when do we use queuing network model, right? So first, we have a simple software execution graph or software execution model, and if we don't detect any performance issues, then it's time for us to construct a queuing network model. Okay. So what are the benefits of a queuing network models or QNM? First, it provides more precise metric that account for resource contention, account for multiple users. Also, it is sensitive to the variation in workloads composition. So if you have more users, the result will be different, right? And also, it can allow you to understand the scalability, allow you to understand how many users the systems can handle, and also allow you to set up or meet your service level objectives. What is service level objectives? For example, users need to be able to access your system within like 1 millisecond. That's the service level objectives. Right? And it helps you to identify bottleneck resources. Also provides you the options to improve your system. For example, you identify a bottleneck, then you want to add more resources to this bottleneck. Okay. So one main characteristics of queuing network models is that it considers the resource contentions. So what are resource contentions? So there are multiple sources for resource contentions. The first one, multiple users using one application or one system at the same time, right? For example, when several ATM customers do a withdrawal simultaneously, then each of them will access the database at the same time, right? But maybe the database can allow just one access at one time, right? So there is a resource contention. So one need to wait for another to finish in order to process. This is the first source of contention. Second source of contention is so multiple applications or systems executing on the same hardware resources, right? Two applications using the CPU, so there will be resource contentions. And the application under consideration can have separate concurrent processes. They can have resource contention, and also multi-threading can have a resource contention. Okay, so what is actually the basic component of a queuing network model? So basic component is a queue. So what is a queue? If you look at the figure on the right, it is a queue. It's a basic component of a queuing network. This queue is also referred to as a service station or service center. It has two parts. It has a waiting line and a server, right? The waiting line basically is it's like so when you want to visit a clinic, right? You wait in a waiting zone, right? At least like this waiting zone. The server is actually when you actually talk to the doctor, that's a service time. So this is server. In software systems, the server can be one CPU, one disk, one network unit, right? So the entire thing, waiting line and server added together is a queue, right? So queuing network models represent every basic component as a queue, okay? And here we have some concepts about time, right? What wait time. So the time you spend in the waiting line is a wait time. Service time is when you actually when the request is actually processed by the server, for example, the CPU or the disk. Right? And there's residence time. Residence time is adding wait time and service time together. It's a residence time, which is the time from the arrival of the request to the queue until the departure of the request from the queue. Okay. So this is a queue. So queuing networks models is basically to do computations on these queues or on a compilation of queues. So what are the calculations? What are the performance metrics we want to calculate? It's the same. We have the similar performance metrics we already discussed again and again, right? So there are several performance metrics of interest for each server or each queue, right? The first one is residence time, we already talked about. It's the average time jobs spent in the server, in service and waiting, right? Average time spent in a queue. Utilization is the average percentage of the time the server is busy, right? The server may be idle sometimes, right? When there's nothing in the queue, it's idle, and it can be busy, right? The percentage of busy time is utilization. Throughput is average rate at which jobs complete service. For example, if this server handles 1,000 requests in each second, so the throughput is 1,000, right? And queue length is an average number of jobs at the server, including those are receiving service and those are waiting. It's a queue length, right? So the average number of jobs in a queue, the queue length. Okay, please remember those letters representing each concept. RT for residence time, U for utilization, X for throughput, N for queue length. Okay. A queue networks, to analyze the queue networks, basically to calculate this metrics. Okay. So how to calculate this matrix? So this matrix depends on the number of jobs, the amount of service they need, and the time required for a server to process individual jobs, and the policy used to select the next job from a queue to process, right? So we will see concrete examples. But first, let's look at a data, right? So we have a data in mind, then we can do the explanation of this matrix. Okay. This is the execution profile. Here we have a time. The horizontal axis is the time in seconds, and the vertical axis is the number of jobs, so which indicate the number of jobs in the queue at this time, right? From this figure, so I want to ask you some questions. The first, what is the total measurement period? You can say 21 or 20, right? Here we just consider 20, right? 20 seconds is our entire measurement period. What is a busy time? So busy time is whenever there is at least one job in the queue, right? We see 16 seconds, right? Among this first 20 seconds, there are 16 seconds where there are at least one job, right? So busy time is 16 seconds. What is the number of arrivals? What is the number of completions? Here we need some imagination. You can consider there are, so this profile is not a deterministic for you to know the arrival and the completions numbers, but here you can consider 8 arrivals, 8 completions. So why 8, right? So I'll to briefly show you like, so here the first time in this second, there's one new job, right? Here another new job, there's another new job, 3 new jobs, and there's no new jobs, maybe. Here 4 new jobs, probably at this second, one job was finished. Here add one more, 5 new jobs, 6 new jobs, right? 6 jobs, and each job will finish after that. And there's no job, right? So here we have a 7th new job, right? 8 new job, so 8, but it doesn't have to be 8, but we can consider 8. There are 8 new arrivals and 8 completions, right? Then we do, based on these numbers, we do some calculations of the performance metrics, right? So first, what is the utilization rate? So utilization equals to busy time divided by total time, right? This is utilization. Throughput equals to the completed jobs divided by the total time, right? So utilization is U, throughput is X. So mean service time. So mean service time is the total busy time divided by the number of jobs completed. Mean service time, right? And so this area under the graph, it's a basically intermediate metric, right? So area under the graph here, the area under the graph is basically the gray area, right? It's a sum of the jobs at each time. Sum of jobs in the queue at each time. A residence time. So residence time is the area under graph divided by the number of completed jobs, right? So because the area under graph is basically the total, is a sum of the number of jobs at each time, right? So when you divide the number of jobs completed, the residence time. Right? Here you need some logic here, calculation. So if you have any questions, you can ask me, so we can do the math. Okay. And there are also reference books if you want to check why it is this way. Right? And we have a queue length. Queue length is an area under graph divided by the total time. Okay. The queue length is the number of jobs in a queue, right? So here, all these all these variables are average values. We calculate the average values. In this example, in this concrete example, we know that the total period is 20, complete job is 8, busy time is 16. So our utilization is 0.8, B divided by T is 0.8, and our throughput is 0.4 because it is C divided by T is 8 divided by 16, right? Sorry, 8 divided by 20 is 0.4. The mean service time is B divided by C, busy time divided by completed jobs is 16 divided by 8. Area under the graph, you can count, right? So for example, in this second, the first second with jobs, there are 1 job, second with jobs, 2 jobs, 3 jobs, add them together is 41 jobs. The residence time is W divided by C is 41 divided by 8 is a 5.125, right? Q length is W divided by T is a 41 divided by total period 20 is a 2.05. I know there's lots of mathematics here, but if you have any questions, you can ask, okay? So here, actually, we have this, we already collected data, right? We know how many jobs each time, right? But in fact, when you are building a model, you don't have this data, right? So you want to, so you're not measuring it. Actually, you're modeling, you're simulating it. So for example, how can we get the number of jobs at each active jobs at each time, right? You don't know this. So here, this execution profile is just for us to understand how to calculate this performance metrics. Okay. So actually, how to solve queuing method. So how to derive the execution time, right? We need 2 things. First thing is we need a workload intensity. And second thing, we need service requirements. So what is workload intensity? It is a measure of the number of requests made by a workload in a given time interval. For example, 1,000 visit to this CPU in 1 second. So the workload intensity is 1,000, okay? What is service requirement? Service requirements are the amount of time that the workload requires from each of the devices in a processing facility. For example, the CPU needs 1 millisecond to process one request or 1 visit. That is a service requirements, because this visit or this request needs 1 millisecond of CPU, right? As a service requirement. After we have the workload intensity and service requirements, so basically, you know, like how often this system will be accessed, right? And for each access, what is the time needed? Then you can calculate the total executing time, right? So that's what we need as input for queuing model, okay? Let's go to details and see examples about how we solve a queuing model. So we have some assumptions first. We should assume that the system is fast enough to handle the arrivals. Therefore, the completion rate or throughput equals the arrival rate, right? So when you have 1,000 visit, 1,000 requests, or 1,000 arrival in 1 second, then the departure rate is the same. So in 1 second, you finish 1,000 requests. Throughput is also 1,000, right? So this part is called a jobs flow balance. So you don't accumulate a backlog there. So so your departure rate equals to your arrival rate. That is our assumption. Okay. Example here. Arrival rate is 0.4 jobs per second. This is equal to the completion rate of throughput, right? And the service requirements is 2 seconds. So each job will need 2 seconds to process, for example, in the CPU, right? So these are inputs, worker intensity, and service requirements. So based on these two inputs, we want to calculate the metrics such as throughput, utilization, residence time, queue length, right? So what is the throughput? Throughput is equal to arrival rate, right? So we use X to indicate throughput. So lambda is used to indicate arrival rate, right? And the S is used to indicate mean service time. Utilization. There's a law called utilization law. Basically, it shows that the utilization equals to throughput times the service time, the mean service time, right? So basically, this means that if you tell me like how long one single request needs, right? Like here, 2 seconds is needed for one single request, right? And how often your requests are, then I can tell you your CPU or your other disk utilization, right? So we'll give concrete examples later. Residence time, RT equals to the mean service time divided by 1 minus the utilization. Yeah, here you probably need some time to digest this, okay? And yeah, if you have any question, we can discuss later, okay? For now, you can just know there's such a equation here. Queue length equals to throughput times residence time, right? So basically, the queue length is your arrival rate times how long one request reside in this queue, right? Then this is the number of requests in this queue. This is called Little law, right? We will show an example. Let's do exercise. Use of utilization law, right? Remember, utilization law is the utilization equals to throughput times the mean service time, right? So please do this exercise. Give you 2 minutes, okay? And tell me your response or your result. Can anyone tell me your results? Okay, let's remember that utilization equals to throughput times service time, right? Let's look at utilization equals to throughput times service time, right? So here, what is the throughput, right? A network segment transmits 1,000 packets per second. 1,000 packets per second. This is a throughput, right? What is the service time? Each package has average transmission time equals to 0.15 milliseconds. This is the service time, right? So we just use 1,000 times 0.15 millisecond. So this millisecond need to be transferred to second, right? So 1,000 times 0.00015 equals to 0.15 second. Oh, sorry, 0.15 or 15%. That is the utilization of the segment. Okay. Any questions here? Next, another exercise is a utilization of a Little law, right? So what is a Little law? Let's go back. Little law is about the length of the queue, or queue length, equals to throughput times residence time. Look at this exercise, and I give you another 2 minutes. You can do this exercise and tell me your results if you have, okay? Okay, can anyone tell me your results? Okay, so I will tell you the answer. Okay, first we calculate the throughput. What is the throughput, right? Because I 10,800 operations performed in 30 seconds, right? So we use 10,800 divided by the time, 30 minutes. 30 minutes transferred to seconds, 1,800 seconds, right? So it's 10,800 divided by 1,800 seconds, which is 6. Throughput is 6. What is the queue length? Because the average number of active NFS requests was found to be 3, which means the queue is 3, right? There are 3 active requests in this queue, right? Some in the waiting zone, some actually served, 2 in the waiting zone, 1 actually served, right? So that's queue length. So because queue length equals to throughput times residence time. So residence time equals to queue length divided by throughput, which is 3 divided by 6 is 0.5 seconds. Okay. Just post this result in chat. Okay. Did I show the result? Okay, yeah. it's unchecked for this. And also, for the previous question, this is for a previous question, okay? This is for this utilization law, and this is for the use of Little law, okay? So yeah, we have some exercise about how to calculate performance metrics based on the workload intensity and the service requirements, okay? So that is for one Q, right? We didn't touch queuing network models yet. So what is actually a queuing network model or QNM? It is in fact a network of queues, right? We talk about what is one queue, a network of queue, or two or more queues connected together. They consist a queuing network. A QN consists of two or more queues that are connected together and serve requests sent by clients. Okay. If you look at this figure at the bottom, you see here we have three queuing networks, or we have three queues, right? The first queue is you see, is a CPU queue, right? We have a waiting line and multiple CPUs. Here we call it a multiple core CPU or multiple service queue, right? So one queue can have one service or multiple service. Here is a multiple service queue. And we see there's another queue for disk, right? And we have a queue for network, right? So what does it mean here? And we see some numbers, 0.8, 0.2, right? What does it mean? So here, it means we see arriving request and a departure request. We see that, so when there are requests arriving in the queue network, it first will pass through a multiple core CPU. This is a multiple server queue, right? Then there's the probability of 0.8 to go through a disk queue, and the probability of 0.2 to go through a network queue before it leaves the queue, right? And also there is a probability to go back to the start of the queue, right? So this is a very simple queuing network, okay? So there are three types of queuing networks, or three types of QNM, queuing network models. The first one is open models. The requests come from a source that is external of the queuing network and leave the network after service completion. Closed models, there's no external source of requests. There's no departure request. So just the request just looping inside the model. Okay, the mixed models. It's open for some workload classes and closed for others. So it's mixed models. So here, this is an open QNM. Okay, we see there's a external input and external output, right? There's a arrival and departure, both are external. It's open QM. So OpenQM is appropriate for systems with external arrivals and departures, such as ATM or ATM. You have the customers to use this machine to insert a card, right? So those are external arrivals and departures. So for an OpenQM, we need to identify or to specify the workload intensity and service requirements in order to calculate the performance metrics of this queuing network. Okay. So what is a workload, right? Workload is the same as arrival rate. It is at the rate at which jobs arrive for the service. Okay. What is a service requirement, right? Service requirement, you can either specify the number of visits and the average service time per visit, right? Because for one request, there may be multiple visits for one server or one computing device, right? For example, when you are search something on Google, you may visit the CPU 100 times, right? The multiple visits. You can either tell me the number of visits for each device and the average service time per visit, or just tell me the total demand for a device, which is the total time for the on this device for this request. So how we do this OpenQM computation is similar to what we do for a single queue, right? Except that we have multiple queues, right? So we have it's a little bit more things here. First, we specify some parameters. Lambda is a service system arrival rate, the same as before, right? And VI is the number of visits to the device. Device I to device I, right? SI is the mean service time at the device I. Right? We have, for example, in this simple example, we have 3 devices: CPU, one disk, and one network. Okay. And the system throughput x0 equals to arrival rate, which is lambda. And the throughput of device I is, which we write it as xi, right? Is x0 times vi, right? You have the whole throughput of the system, and within each request, you visit one device multiple times. So the throughput of the device I is the throughput of the entire system times the number of visits per request to this device. Okay. Utilization of device, same as utilization law, right? It is UI is equals to the throughput of this device times the service time of this device. Residence time per visit, similarly, RTI equals to SI divided by 1 minus UI, which is SI is the mean service time, and UI is the utilization of this device. Okay, lots of mathematics here, you know. And we have others. Q length, right? We remember that little law. So first, Q length of each device equals to the throughput of the device times the residence time of the device. And the system Q length equals to the sum of the Q length of each device. For example, you have multiple requests. Some are waiting for CPU, some are waiting for disk, some are waiting for network. Then the entire queue is everything added together, right? That is a system queue length. And system response time, again, the little law, right, equals to the number of requests divided by throughput. Oh, sorry, not the number of requests. N is the system queue length divided by throughput. This is a system response time, okay? I know it might be hard to digest all this mathematics. You probably need to review this later, okay? Let's give a concrete example to make it easier to understand. So here, we give this 2 inputs, right? One is workload intensity. So one is service time, right? Or service requirements. What is the workload, the workload intensity? So we give the system arrival rate, which is 5 jobs per second. 5 jobs per second. And for service requirements for each device, we give the number of visits and the service time for each visit, right? For CPU, one request would have 5 visits to CPU, and each time, each visit, we need a 0.01 seconds on the CPU, okay? And similar for disk 1, disk 2, okay? Then we do a calculation. We calculate the metrics, throughput, response time, utilization, things, right? Then how we do the calculation? Yeah, here I'll just show an example and tell you why it is the result, okay? A throughput, first, for each device, there's a throughput, right? CPU is 25, why is 25? Because the system throughput is 5, and each visit or each request will have 5 visits to CPU, so it's 5 times 5, which is the throughput for CPU. For disk is 15 is a 5 times 3 disk, and the throughput for disk 2 is 5, okay? And the service time CPU, right, is 0.01. Why it is 0.01? It is a mean service time 0.01 is written here, right? 0.01. And similar for disk 1, disk 2. A utilization for CPU is a 0.25, right? Utilization is a throughput times service time, right? Is a 25 times, for CPU is 25 times 0.01, so it's 0.25, okay? And similar for disk 1, disk 2. For residence time, right? So to remember residence time, what is a residence time? Residence time equals to, let's show the similar here. So residence time for each device equals to the service time divided by 1 minus utilization, right? So the service time is 0.01 for CPU, and 1 minus utilization is 1 minus 0.25. So it's 0.013 for residence time for CPU, right? And then we calculate QNAND, right? QNAND, just remember, QNAND is this one is throughput of the device times the residence time of the device. This is QNAND, right? For this is the QNAND for CPU, right? Then we calculate QNAND of disk 1, disk 2, right? Then adding them together, all the QNAND together is a QNAND for the entire system, or the total jobs in your system, right? Is 0.325 plus 0.825 plus 0.111 equals to 1.26. This is a total QNAND, or total jobs in your system. Then we calculate the system response time, which is total QNAND divided by total throughput, right? Is 1.26 divided by 5 is 0.252 second. This is the system response time, okay? So do you have any questions here?
No, here there is no question.
Okay, thanks. So let's continue. Here I have one exercise. You don't need to do it here. So I want you to do it after the class, okay? What if we change the arrival rate from 5 to 10, right? We double the arrival rate. Then I want you to calculate the metrics. Eventually, I want to calculate the system response time, okay? Just follow the same formula, okay? This is for open QM. So what about for closed QM? This is a closed QM. You see, there's no external inputs, outputs. Just the requests are circulating within the queue network. Okay. And what we need, right? We need still two things: workload intensity and service requirements. Workload intensity, the number of users in this network, right? Number of users circulating, and a number of simultaneous jobs. And we need something like called think time, the think time, right? Because when you have external arrival rate, you know there's a certain rate, but if there's a circulating within the loop, you probably need some waiting time, right? Because it's not just after departure, go back to the arrival part immediately. There's a think time, you need to wait. Think time is something like, so when you are sending an email, right? When you are, after sending one email, before sending another email, you need to have some, if you are a human, you need some time to think. There must be some delay, right? It's a think time. With number of visits, same for the OpenQM service time, right? Similarly, a total demand for each device, which is a number of visits times the service time, okay? We don't go to details for closed QM here. It's a very similar. It's the same steps, okay? And so we talk about how we solve the QM models, right? But there's one thing. What is the service time? We give the service time, right? And we give this workload intensity. Workload intensity is easy to understand. We just how to say? We have a service agreement with our customer. We say we need to handle 1,000 users per second. That's a service agreement. But how about service time? How long does it take for the CPU to handle this request, right? What is the service time? How is it calculated, right? Basically, we have some steps, right? So I'll go to it later. Here we see how to, basically this is about how to derive system model parameters from the software model results. Okay. The first step is to have this Q network model to complete our model topology, to complete the graph. Okay. Second step, to decide whether we use an open or closed QM. The third step is determine the workload intensity for each scenario, right? Fourth step is to specify the service requirements. Here we'll go into detail about how to specify service requirements, right? Let's see this example the same. This is the example for the auto transition scenario of the ATM, right? We remember this one. On the left, we see the software resource requirements for each step. On right is a process and overhead matrix, which map the software requirement unit to the hardware units, right? And then how we do the calculation of the service time, right? So we first look at for each basic step, right? Each basic step, how many hardware resources they need. We already did this calculation before. We just a review, right? For example, for validate user, we calculate and we get 1,020K instructions for CPU usage and 4 disk IO and 0 message. Okay, and then we sum them together. We get the total number of CPU instructions needed, total number of disk IO used, total number of messages, right? And then we get this information. Then remember, we have this service time, right, for each hardware device, right? Then we calculate. So based on the number of visits, right, and based on the device service time, so we can calculate the actual service time of these different devices, right? For example, for CPU, there are how many visits to the CPU for each request, right? See there, the number of visits 3,000 110, 3110, right? This number of k instructions. For disk is 14. For network message is 1, right? Those are number of visits per visit. So the service time is a per visit time needed. So then we can actually combine them together to multiply this two to get the service time of each device, right? For CPU, we already had this multiplication. 0.0311 is a multiplication of the service time of a CPU for each visit times other visit, more than 3,000 visits. For disk, is 14 times 0.02. For network, is 1 times 0.001, right? So these are the service time for each device, right? Then we get this and we get workload intensity, then we can compute the total, the performance metrics. For example, the response time of this entire system, right? So any questions here? Okay, so if no question, I'll just so there are a few hints for the queuing network models. Right? The first hint is so we need to consider a scenario of multiple users and workloads, right? So we specify the workload intensity of things. And the second one is using queue networks, we can only capture average performance metrics. We don't calculate the peak performance, right? And for sensitivity, it is if a small change in one parameter causes a large change in the output metrics, the model is sensitive to that parameter. Okay, sensitivity and scalability. So after you do the model, so you can do the calculation about if you increase your loads, what is the response time, right? So based on this, you can add more resources if the response time, anticipated response time is not good, right? Bottlenecks, similarly, you can identify the bottlenecks based on the model. Okay, so this is all about queuing network models. There are lots of mathematics. Okay, let's have a short break. Let's have a break of like 4 minutes, right? Then we meet at 3:10. Okay, then we will briefly discuss machine learning based performance models. Okay, for 3:10, right? Let's meet 3:10. Okay.